Alright, in this video we are going to discuss how to get force from a potential energy function. And the biggest complication of doing this is that force is a vector and potential energy is a scalar quantity. And remember, we're in essence getting from force to potential energy through work. So work is equal to the negative change of potential energy. And work is equal to the integral of the force function in terms of x. So in essence, in order to find a potential energy term, we're doing an integral. So you would think to get force back, you would simply take a derivative. But the issue is that from the potential energy function that is a scalar term, you have to extract not only the magnitude, but the direction of the force, and that leads to some layer of complexities. Now, it's not so bad whenever the potential energy function is a function of r. That sort of idea that it merely depends upon its distance from the center of the object exerting the force. So remember, potential energy is energy stored relative to a baseline, so there's always going to be that distance dependence in there. But if it's distance dependent is along just one line, so your r line, it isn't so bad. You just simply take the derivative, understand that it acts in the radial direction. What gets more complicated is when the force has an xyz dependence, and the potential energy therefore has an xyz dependence. So we have to extract back out the amount of the forces in the x direction, the amount of forces in the y direction, and the amount of the force that is in the z direction. And we do this by taking something called the gradient. And you can sort of think of gradient like the grade in the road, like you're looking at how much the slope or the road slopes. You can also think of it as something like a topography map, where you're getting a mountain and you're seeing how the elevation of the mountain changes over 3 dimensions. And so, in order to do this, we have to flush out that x, y, and z component. In order to do that, as I said, we're taking the gradient. It involves another Calc 3 concept called taking a partial derivative. And partial derivatives are very similar to taking regular derivatives. But we're recognizing the fact that the potential energy function here could be dependent upon an x, y, or z component, and could be some combination of the 3. So when you take a partial derivative, you're taking a partial derivative in terms of one specific variable. So in the first term here, it's going to be in terms of x. So you're going to pretend like all the other items in the function are constants. So if it's a y or a z or a 5, you treat those all the same. And that gives you your x term. To do your y term, you're going to take the partial derivative in terms of y. So if it's an x or a z or a constant number, you're going to treat those all like constants. And then to get your z term, you're going to take the partial derivative in terms of z. So you're going to pretend the x's and the y's and the numbers are all constants, and just treat z like it's the only variable. So you'll end up with an x term, a y term, and a z term, and you can see now what direction the force points in, to which quadrant. And you can use Pythagorean's theorem in order to figure out what the magnitude of the force is. But you do have to go back through and see how that slope or how the potential energy function is changing in each direction to see what direction the force actually pointed in.